Hi, everybody. My name is Dustin Madison. I'm a postdoc working at West Virginia University, and I study nanohertz gravitational waves. It's an extreme honor to have been asked to give this talk for the LISA Symposium. And without further ado, I'm just going to go ahead and get into my slides here. So, the title of my talk is Knocking at the Door, the Current Status of Pulsar Timing Array Science. And specifically, I'm going to be talking about the results from the NANOGrav collaboration, of which I'm a member. So what is NANOGrav? Well, it stands for the North American Nanohertz Observatory for Gravitational Waves, and it's a collaboration of about 100 people who are radio astronomers, gravitational wave experts, data analysts, and supermassive black hole specialists. In 2016, we were recognized by the National Science Foundation as a so-called Physics Frontiers Center. The Physics Frontiers Center is a line of funding dedicated to mid-scale collaborations that are distributed across many institutions and are working on what the NSF deems major scientific breakthroughs. We began collecting data in 2004 using our two telescopes, the Green Bank telescope and the Arecibo telescope. And since 2004, we've continuously ramped up our operations so that now we're regularly monitoring over 70 millisecond pulsars, requiring upwards of 1,000 hours of telescope time per year. So you may have recently seen there was some damage to the Arecibo dish caused by a compromised support cable. Our observing program is occasionally interrupted by things such as this, but our utilization of two world-class facilities safeguards our scientific program, and NANOGrav diligently promotes the ongoing support for and development of our telescopes. Now, we're not in this alone. Since our inception, we've been working with our partners overseas in Europe, the European Pulsar Timing Array, or EPTA, and in Australia, the PPTA, Parkes Pulsar Timing Array. In recent years, there have been pulsar timing array efforts that have started in India, in China, and in South Africa. And together, we operate under the sort of umbrella organization called the International Pulsar Timing Array. Now, how could we potentially detect gravitational waves through pulsar timing? So we're here on Earth orbiting a very happy sun, and we're observing these millisecond pulsars. So most of our pulsars are orbiting white dwarfs, and they're sending us these little pulses of radio waves, okay? Now, with our world-class radio telescopes and some very sophisticated modeling of the pulsar systems, we can track the phase of our pulsars' pulse trains. And by that, I mean, we're counting every single pulse that comes from our pulsars, okay? We can track the phase with approximately 30 nanosecond errors over decadal timescales. So that's the type of precision measurement we're talking about. Now, how does the gravitational wave enter into that? So this top equation is what I'm saying is the gravitational wave, h sub I j, and it's equal to just some polarization tensor epsilon times h, some solution of a wave equation. Okay, and this gravitational wave causes a redshift. It causes our pulsars to appear to pulsate at slightly different frequencies than what is intrinsic to them. And so this redshift z, you take two copies of this unit vector in hat. In hat is the vector pointing from the Earth to the pulsar we're observing. You contract that with this epsilon tensor, and then you divide by 2 times 1 plus p hat dot n hat. P hat is the direction in which the gravitational wave is propagating, and again, n hat is the direction to the pulsar. In brackets, there's this difference of these two terms. On the left, there's something called the Earth term. The Earth term probes the gravitational wave field at the local time and at the position of the Earth, okay? And then you subtract off something called the pulsar term, which is evaluated at the position of the pulsar at some delayed time. And the amount of delay depends on the distance to the pulsar. Now, the Earth term is correlated among all pulsars because it's probing the local gravitational wave field. But the pulsar term, since the delay in the pulsar term depends on the distance to our pulsars, which we don't know incredibly well, the pulsar term effectively acts as a source of noise that's roughly as big as our signal, the Earth term signal. And so in order to overcome this source of sort of self-noise, we have to observe many pulsars to overcome this. And that also helps us to pull out the sort of correlations in the Earth term signature. And as I mentioned, we're tracking the phase of our pulsar's pulse train, not the frequency. So we're actually sensitive to the integrated frequency shift. This enhances our sensitivity to lower frequencies and makes it so that our sort of sweet spot in our sensitivity is around a nanohertz or several nanohertz. So I'm mainly going to be talking, or I'm going to be talking a lot at least, about results from our 11-year data release, which came out in 2018. Putting together this data release, all the observations that went into it, all the curation of the data was a big effort that was led by Professor David Nice. And so let's give him credit right off the bat. So I'm going to discuss many results that came out of this data release, but first let me talk about some elements of the data release itself. So here's a snapshot of the full data release. Every little circle in this plot represents about 30 minutes of observation time of a particular pulsar. The different colors, they indicate different radio bands, so we tend to do observations at multiple sort of sections of the radio frequency spectrum, and our different telescopes, Green Bank and Arecibo. We only included pulsars in this data set for which we had at least 3 years worth of observations. So we actually observed more pulsars than the 45 pulsars that were included in this data set. Now here's a sort of more detailed breakdown of one of our pulsars, pulsar J1909 minus 3744. Now this pulsar is arguably one of the best known pulsars for precision timing. This top panel shows our sort of channelized measurements. So because of the high sensitivity of our very big telescopes, we can record many times of arrival, we call them, across our radio frequency band. Okay, with these channelized times of arrival, we're able to measure sort of chromatic effects that are caused by intervening interstellar and interplanetary plasma, mostly so-called dispersive delays. So by using wide bandwidth instruments, we're able to correct for these dispersive delays. Once you correct for those dispersive delays, you can average our channelized measurements across the band, and you can start to see some sort of low frequency structure pop out of our so-called timing residuals here in the second panel. So this low frequency structure that you can kind of see here, I mean, that could just be intrinsic to this pulsar. Pulsars sometimes do this sort of low frequency wander in their rotational behavior. This could also possibly be gravitational waves. The only way to tell which is to observe many pulsars and to look for correlations in their timing residuals. Now this low frequency structure, we can sort of remove it by modeling it, and we model it as a power law, as this equation describes. Now we call this red noise, and we do red noise modeling on a per pulsar basis. Once we do that, we can start to look for gravitational waves. So the first real result I'm going to talk about is from this paper, limits on gravitational waves from individual supermassive black hole binaries. Okay, so we used our data set to look for evidence of nearly monochromatic gravitational waves from individual supermassive black hole binaries. And it's supermassive black hole binaries that are really the sources we're interested with in NANOGrav. Okay, so this plot shows, it shows what I said earlier, that our sensitivity to gravitational waves tends to improve as you move to lower frequencies. And that continues until you hit around 7 or 8 nanohertz, and that's when you start to get this upturn in the spectrum again. Now that's because we have to do certain modeling of our pulsar's spin parameters. And there's also a spike at an inverse year that also has to do with some modeling that we have to do for our pulsar systems. Now the 3 different curves in this panel, they show that as we increase the length of our data set from 5 years to 9 years to finally 11 years, which is what we analyzed in this paper, our sensitivity just increasingly, or it improves at every stage, okay? Now, if you look at how our sensitivity varies across the sky, you see that we have incredibly asymmetric sensitivity on the sky. And that's just because our sensitivity is better in the direction of most of our pulsars. And because our solar system is on the outskirts of the Milky Way, most of the pulsars we observe are towards the galactic interior. And that is just a fact of nature. I think we are always going to have this sort of asymmetric sensitivity on the sky, okay? But what this plot also shows is that in our direction of sort of peak sensitivity and at our peak frequency, or at our best frequency, we could potentially detect a binary with a chirp mass of 1 billion solar masses out to about 120 megaparsecs. So I want to give credit to the corresponding author on this paper. This work was led by Professor Sarah Vigeland. So we also can target specific systems that for some reason, maybe in electromagnetic observations, we think is particularly interesting. And that's what we did in this paper here, multi-messenger gravitational wave searches with pulsar timing arrays, an application to 3C66b. 3C66b, it's a nearby galaxy. It's about 85 megaparsecs away. And years ago, people noticed that there's some apparent elliptical motion in its core. If you look at the core with VLBI, you see this sort of elliptical motion. And this was potentially indicative of the dynamics of a supermassive black hole binary. And if that were the case, depending on the chirp mass of that binary, it would be radiating very loud gravitational waves right in the nanohertz band that we're probing with pulsar timing arrays. And so in the past, estimates for the chirp mass of this potential supermassive black hole binary, they've already been reduced in order to not be in clear violation of previous pulsar timing array non-detections. So in this paper, what this figure shows, the reduced mass estimates based on electromagnetic observations are indicated by this sort of tangerine shaded region. Okay, the histogram is our posteriors on the chirp mass from the system based entirely on our pulsar timing array data. Okay, now you can see our posterior goes all the way down to a chirp mass of 0. That indicates we have not detected gravitational waves from this system. But our 95% confidence limit is starting to get really close to the estimates based on electromagnetic observations. So we're beginning to encroach on even this revised down chirp mass estimate. So knowing the precise location of this object we're targeting really improves our sensitivity, our strain sensitivity by about a factor of 2. And because you can get the electromagnetic observations give you a prediction for the frequency of the gravitational waves, that actually allows us to constrain the chirp mass by about a factor of 10 better than we would be able to do if we didn't have a specific prediction for the gravitational wave frequency, okay? Now what this panel is demonstrating, well, what it's showing is, in this paper, we developed some techniques for more flexibly incorporating less comprehensive electromagnetic knowledge of a source into a targeted gravitational wave search. So this could help in the future to rapidly assess whether or not we detect gravitational waves from a candidate supermassive black hole binary that's flagged for something like photometric variability or maybe a morphological tracer such as a displaced core. Okay, so there's really a bright future for these multi-messenger opportunities with pulsar timing arrays. Now this work was led by a graduate student at West Virginia University named Caitlin Witt. So among single source searches, the last one I'm going to talk about from the 11-year data set is this burst with memory search, okay? So a gravitational wave burst with memory is generated in the violent sort of final merger of a supermassive black hole binary. And though those events are anticipated to be extremely rare, if one were to occur during our observing span, we could potentially detect it. So this plot shows that during our observing span, well, between roughly 2006 and 2014, if you marginalize over the sky and orientation parameters for a merging system, we can rule out the presence of any bursts with memory with a strain exceeding about 10 to the minus 13, okay? But in this 11-year data set, we also reanalyzed our 9-year data set. So if you look at this bump in our 9-year limits, that bump was tied to a sort of anomalous feature in the 9-year data set that looked a lot like a burst with memory. So the anomalous feature, what this plot shows is how much each of our pulsars sort of supported this anomalous detection of a burst with memory, okay? Only 2 of our pulsars really seemed to prefer this weird anomalous burst with memory looking signature. The rest of the pulsars in our 9-year data set were sort of agnostic. They either kind of marginally said this signal looked like it might be real, or some of our pulsars outright disfavored this signal model. So with a full analysis of the improved 11-year data set, we were able to finally put to bed this anomalous 9-year burst with memory feature that sort of popped up. It's not a real gravitational wave event. Okay, so this important work was led by Paul Baker, Professor Paul Baker from Widener University. Okay, But what kind of signal do we really think we might detect? So I said a few slides ago, our peak sensitivity is around 7 or 8 nanohertz currently. And our best sensitivity is only going to march down to lower and lower frequencies. So if you look at this synthetic spectrum based on a population synthesis model of supermassive black hole binaries, down at the 7 or 8 nanohertz regime, you start to run into this confusion-limited stochastic background rather than bright individual sources, okay? So down in this nanohertz band, this confusion-limited stochastic background, we're probing sort of population-wide ensemble properties of sort of future LISA sources in their adolescence. So some of these sources over their lifetime could evolve into sources that would merge in the LISA band. And so this is an important way in which NANOGrav and LISA can talk to each other. So what's sort of the science or the physics that makes a stochastic background? Okay, so this is an equation that was generated by Phinney back in 2001. He talked about the so-called characteristic strain amplitude, this h sub c. So the square of it in a universe of circular gravitational wave driven coalescing binaries is equal to this equation. So these parts of this equation, they're really just what general relativity predicts for the radiation given off by these circular gravitational wave driven binaries at a certain redshift, okay? So you integrate over systems like that. It's this part where a lot of the astrophysics enters in. So this is the differential density of merging systems per unit redshift and per unit chirp mass, okay? This is highly unknown. There's many models for this, but the predictions from this, or predictions for this, can lead to pretty wide predictions for what the amplitude of this stochastic background's characteristic strain amplitude should be, okay? Another important assumption in this is this circular gravitational wave driven assumption. So a lot of additional astrophysics also enters in here. Many of the sort of open questions on this topic, whether or not this is actually going to be explanatory of the real signal in nature, those get lumped together under something that's called the final parsec problem. So the final parsec problem, it's basically this. We don't know exactly how supermassive black hole binaries get from sort of picohertz gravitational waves where they're separated by over a parsec into the nanohertz gravitational wave band where they can efficiently radiate gravitational waves. And eventually, through emission of gravitational waves, be driven to merger, okay? So yeah, the binaries, they certainly need to get into the nanohertz band in order to ever sort of evolve into the LISA band. So how, if the final parsec problem is solved, is a big question that pulsar timing arrays can potentially interrogate, okay? And I think that's what I just said. So how the final parsec problem is solved, it affects the low frequency end of the nanohertz part of the gravitational wave spectrum. So around 1 nanohertz, you can start to see roll off in the power of what is otherwise a power law spectrum at higher frequencies. And the exact properties of that roll off depend on what mechanisms go into solving the final parsec problem. Is it 3 body interactions with another supermassive black hole? Is it excess gas in the innermost cores of galaxies? Is it just that eccentricity is particularly important in the early evolution of supermassive black hole binaries? We don't currently know, but we could potentially probe that with pulsar timing arrays. And that's a big part of why the sort of long-term characterization of the nanohertz gravitational wave spectrum is so important. It's here that we may find the solutions of the final parsec problem. So how do we search for a stochastic background? Well, we look at pairs of pulsars, okay? So a stochastic background, it induces partially correlated timing behavior between pairs of pulsars. So if you look at a pair of pulsars, you can correlate their timing residuals. And depending on the angle between those 2 pulsars, there's this specific prediction of general relativity for how much the timing residuals should be correlated by how much the timing residuals should be correlated between those 2 pulsars. And the amount of correlation is called the Hellings and Downs correlation, okay? So we looked for this. We looked for a stochastic background from, we looked for these Hellings and Downs correlations in our 11-year data set. And as soon as we did, we found that our posteriors on the amplitude for the gravitational wave background were highly dependent on what model of the solar system we used, which is not what you want. So we hypothesized that actually we didn't have sufficient knowledge of Jupiter's mass or its orbital shape, and that was preventing us from knowing the position of the solar system barycenter well enough to do our experiment correctly. So because after all, we need to know where the position of the solar system barycenter is to within just a few tens of meters. Okay, so we need to know where the most massive planet in the solar system is to an extremely high accuracy. So we developed some methods for sort of marginalizing over the orbital elements of Jupiter to arrive at a more robust, ephemeris independent upper limit. And the upper limit we quoted out of the 11-year data set was about 1.5 times 10 to the minus 15, okay? Now, the effort for modeling the solar system and marginalizing over the solar system model, that was, you can find a more detailed description of that in this recent paper that one of the LISA Symposium co-organizers and NANOGrav member, Michele Vallisneri, led. So I encourage you to check that out. But this limit that we set, our upper limit of about 1.5 times 10 to the minus 15, these shaded regions in this panel, they show sort of astrophysical predictions for where the amplitude of the background may lie. And our limit has started to rule out some of the more optimistic estimates for where the background may lie. So by not detecting a gravitational wave background, we're already starting to inform astrophysical models for the population of supermassive black hole binaries. Now this big effort was led by Professor Stephen Taylor at Vanderbilt. Okay, so that's what I wanted to say about our 11-year data release. We have recently, very recently, released a new data release, our 12.5-year data release. And we've actually released 2 versions of it. So one version we call the narrowband timing data set. That's very similar to our previous data sets. It's just bigger and badder. But we've also produced this new wideband timing data set where we've incorporated some new techniques that sort of reduce the volume of our data set. And we're really sort of handling possible chromatic delays from interstellar plasma in a new way. This panel here, it shows the timing residuals for J1909 from the 2 different techniques, the wideband timing and the more traditional narrowband timing, okay? So producing these data sets was another big effort. The narrowband timing result was produced by Megan DeCesar, who is now a AAAS policy fellow working on solar energy. And the wideband timing was produced by NANOGrav postdoc Tim Panucci. So with these these new data sets, we once again looked for a stochastic background of gravitational waves, and we are no longer able to set an upper limit. And that's because we are beginning to see structure in our data that resembles what we would anticipate seeing in the early stages of making a detection of the stochastic background of gravitational waves. So this is work that we are going to be submitting imminently. In fact, by the time you view this video, this may have already been submitted. As you can see from this plot, the lowest sort of fluctuation frequencies that we can probe in our 12.5-year data set, they're beginning to show significant power rising above our white noise floor, okay? The red process that we're seeing, it has an amplitude and a spectral index that's consistent with what one might expect from this astrophysical population of supermassive black hole binaries. Many of our pulsars are showing this. So we're calling this currently a common red process. It's common in the sense that several of our pulsars are showing this red process with the same amplitude and the same spectral index. Now, a few of our pulsars marginally disfavor the presence of this common red process. We do not yet see convincing evidence for the sort of pairwise Hellings and Downs spatial correlations that we deem absolutely necessary before anyone can claim a detection of a stochastic background of gravitational waves. We just don't see this yet. Our posteriors on the amplitude of this common red process, they're centered around 1.92 2 times 10 to the minus 15. Now this result is largely insensitive to our choice of solar system ephemeris, unlike in the 11-year data set. Now that could be due to some recent space missions to Jupiter. We've actually been able to refine our knowledge of Jupiter's orbit. So it appears that our 12.5-year data set is not as sensitive with the newest solar system models. Now this amplitude of 1.92 times 10 to the minus 15, it's actually slightly larger than the upper limit on the gravitational wave background's amplitude that we set in the 11-year data set. In the paper and some forthcoming, in this paper and a forthcoming follow-up paper, we offer some justifications for how this can be based around the sort of choice of priors for how we were modeling red noise in our individual pulsars. We think this is reasonable. So a more quantitative summary of this. NANOGrav's 12.5-year data set, it supports the presence of what we're calling a common red process with a spectral index and an amplitude that are consistent with the gravitational waves from an astrophysical population of supermassive black hole binaries. The Bayes factor for this common red process, when you compare it against just individual timing noise in our pulsars, the Bayes factor exceeds 10,000. So it's pretty significant. When we look for these quadrupolar Hellings and Downs spatial correlations and compare that against this non-spatially correlated common red process, that produces a Bayes factor of only a few, okay, which is definitely not a detection. Like I said, we've not detected Hellings and Downs correlations yet. But other spatial correlation patterns, namely a monopolar and dipolar pattern, which you might expect those from, say, errors in terrestrial time standards could produce a monopolar correlation, or ongoing issues with our modeling of the solar system barycenter's location could produce dipolar correlations. Those correlation patterns are strongly disfavored in our 12.5-year data set. If this common red process that we're seeing is attributable to a stochastic background of gravitational waves generated by a population of supermassive black hole binaries, then the bounds of the 95% confidence interval for the characteristic strain amplitude at a reference frequency of an inverse year are 1.37 times 10 to the minus 15 and 2.67 times 10 to the minus 15. So this exciting piece of work has been led by NANOGrav postdoc Joe Simon, who has recently started a new postdoc at CU Boulder. So looking ahead, NANOGrav's 12.5-year data set contains data that extends only through mid-2017, okay? So we are currently curating our 15-year data set. That's 2.5 years more data and more pulsars. So what this plot shows is if we inject an amplitude similar to what we're seeing, about 2 times 10 to the minus 15, into future-looking simulations of NANOGrav's data. So simulations that are based on the, simulations that are based on our current observing program and the noise properties we see in our pulsars. So if we assume that this amplitude we're seeing is from an astrophysical population of supermassive black hole binaries, then we anticipate evidence of a Hellings and Downs correlated gravitational wave signature with a signal-to-noise ratio of between 4 and 7 in NANOGrav's 15-year data set. So I stumbled because I'm excited by this. These are exciting times. Moving still further into the future, the significance of any possible detection we may see in coming years, it will just continue to grow. And we will eventually be able to constrain the shape of the nanohertz gravitational wave spectrum and potentially gain insights into how the final Parsec problem is solved. So this prediction into the future, this work is, this is forthcoming work from a recent graduate student from West Virginia University, Nihan Pol, who is now a postdoc at Vanderbilt. So that's what I wanted to say. I thank you very much for listening to me. It's an exciting time to be a pulsar timing array scientist, and I'm glad to have had the chance to speak at this LISA symposium. Thank you.